Hello there, and welcome to Programming for Hybrid, Untangling Your Threads, an Intel-sponsored session. I'm Lee Davis, a developer technology engineer at Intel, working on both graphics and CPU enabling. For the last 16 years, I've been working directly with game developers. I'm based in the UK, and prior to joining Intel, I actually worked at several independent games companies in the UK. Recently, I've been working on the Hitman franchise with IO Interactive and Codemasters Grid, along with Intel's own master occlusion culling samples. So today's talk actually split into a couple of sections: an introduction covering some of the hardware basics, a section on the OS scheduling and how Windows deals with threads and how it pertains to hybrid, how I do data capture when analysing workloads on Windows, followed by a couple of games case studies, and then some final closing thoughts. Okay, so straight in. What is a hybrid SoC? For Intel, this is a single CPU with two types of core. We call these our performance cores and our efficient cores. These two core types have very different power and performance characteristics, but they both support exactly the same ISA. Our first core type is our performance cores. These are designed around very high instructions per clock tick, where the actual individual throughput of the core is critical. These are for single and limited threaded scenarios. We also have our efficient cores. These are designed to be able to scale out for multi-threaded workloads. They provide better throughput, along with better performance in very power-limited scenarios. We refer to these as performance hybrid, because on the desktop, especially when playing games, we would expect both the performance cores and the efficient cores to be used at exactly the same time to give the absolute maximum performance for the particular game in question. If I change quickly to a block diagram, you can see that each of the P cores has their own L2 cache, while the E cores are built in blocks of 4, with 4 E cores sharing an L2 cache. All of these individual modules communicate via a shared last level cache. Another thing that's worth mentioning at the very start of any hybrid talk for Intel is Intel's Thread Director. This is actually a piece of hardware built directly into the core. Its job is to monitor the instruction mix of any individual thread, along with the state of each core in the system, with a very high level of precision. The idea is this provides feedback to the OS, allowing it to make optimal scheduling decisions based on the workload and any other characteristics in the system. This actual feedback can vary. For instance, the E cores at low powers, especially in a mobile system, can actually outperform a P core for certain workloads. And it is the job of the Thread Director to figure out this tipping point and tell the OS where best to schedule. It's important to note, Thread Director itself doesn't make the final decisions. The OS is responsible for that. Okay, I'd also like to do a quick rundown of Intel's roadmap and how we've got to the point we are today. Going back just a couple of generations, our last desktop system before hybrid actually consisted of 8 P cores, each running at 5.3 GHz, with each P core having 512 kilobytes of L2 cache. The first generation kept approximately the same P core frequency, but significantly increased our L2 cache to 1.25 megabytes. This gave a very large increase in instructions per clock for the P cores. In addition, we added 8 E cores, with each block of 4 having a 2 megabyte L2 cache. And then our second generation moved on further, with the P cores now clocking at 5.8 gigahertz, the L2 cache for the P cores increasing to 2 megabytes, and again a doubling of the actual E cores to 16, with those blocks of 4 now getting 4 megabytes of L2 cache each. It's also worth just pointing out the E cores are themselves very performant. If you compare an E core from today, with running a single thread, to a desktop system from approximately 5 or 6 years ago, the E cores are now already 40% more efficient. So they're more than capable of running gaming workloads themselves. Another topic I'd like to cover is hyperthreading. And this is actually one of the very first slides I ever gave at Intel. Understanding the trade-offs that come with hyperthreading help explain how the OS schedules for E cores later on. The P cores themselves, if we take a simple example running a single thread, the P core will have multiple hardware resources available to it: load, store, multiply, and add units. The P core can also issue multiple instructions in a single clock cycle. But because of dependencies between individual instructions, it's impossible to utilize all of the hardware resources at the same time. If there's more than one thread in the system, then the OS will context switch out and run the second thread sequentially with that. The idea behind hyperthreading was the OS could schedule both threads together and interleave the instructions for both of them. This increases the overall utilization of the hardware resources within the system. An important point to note here, you can see while the overall performance has increased and the number of instructions per clock, or conversely, the clock ticks per instruction, has improved with SMT, on an individual thread basis, and examining the blue thread here, it's actually degraded slightly. The blue thread actually takes longer to complete than when it was running in isolation. And this was one of the design criteria around the E-cores. Although the E-cores themselves run at a lower frequency and have slightly less resources to play with, the idea is an E-core for most threads would be able to complete faster than a P-core if the P-core was fully loaded with two simultaneous threads. This will help explain some of the OS scheduling decisions later. It means we have to change many of our assumptions about writing code on hybrid. The first assumption to question is the basis that all cores would have exactly the same performance profile. This is definitely no longer the case. Even the same ISA can have very different throughput between core types. In addition, not all cores have the same frequency anymore. While both the P and the E cores have different max turbo frequencies, it's also true that even within the P cores, one or two may be running faster than others, and which is the fastest core can actually change over time due to thermals within the system. Another assumption a lot of people would make is if a system supported hyperthreading, then effectively you would double the physical core count to get the number of logical processors. This is also no longer true. The P cores support SMT, while the E cores do not. The final assumption people made was it was only worth optimizing the CPU if you were CPU bound. This hasn't been true for a while, especially with mobile, where optimizing the CPU allows additional power to be directed towards the GPU, increasing the GPU's frequency and helping if you were GPU bound. But it's also true as we've got more and more hardware resources, optimizing some threads, even if they're not the bottleneck, allows the hardware to dedicate more power to the cores that do matter, raising individual frequencies for the highest performance threads within the application. So it certainly helps to optimize anywhere you can to get the best possible performance. The final thing for the introduction is a little bit about CPU topology. Obviously, the topology has got more complex. For Windows, one of the best functions to use is get logical processor information extended. This is a function that actually returns a variable size buffer that you then have to iterate over. The fields we're actually interested in is first of all, any fields that come back as a processor relationship. There'll be one of these structures per logical processor within the system. The most important field in here for us is the efficiency class. This actually ranks the actual logical processor's performance relative to the other logical processors within that system. A system without hybrid, all the cores would have exactly the same efficiency rating of 0. Today on hybrid, we have efficiency class 0 for the E cores and 1 for the performance cores. But it's worth bearing in mind that is not guaranteed to hold true in the future, where there could be more than 2 efficiency classes. So try to avoid making hard assumptions. The other field that's probably interesting is the cache relationship. Although today, each core type will have exactly the same type of cache, with the cache hierarchies being slightly different between the P and the E cores, in future hardware, it's possible there may be a greater variety of cache hierarchies, allowing some cores to have higher performance than others. But between these two fields, you should be able to work out everything that's relevant to the actual hardware in question when you're actually designing how best to schedule your application. Okay, let's move on to OS scheduling. Now, the first important thing to say for OS scheduling is on Windows, there is no central scheduler. Scheduling routines are called whenever an event happens that potentially changes the state of the thread. These type of events include a thread becoming ready to execute or entering a wait state, OS level for interrupts, both timer interrupts and IO completion interrupts. It could be an application-driven event, such as the change of a thread's priority or the change in the thread's quality of service, or it could even be an OS level event, with the OS changing core parking, which we'll talk about later, or Intel's thread director providing updates to the OS which likewise cause the OS to reschedule its threads depending on the current situation the hardware finds itself in. Okay, so moving on, how best to think about threads for application? Probably the starting point is how threads priorities work. A thread has effectively two priority levels, its base priority level and its dynamic level. The base priority level is derived from two things. The first one being the priority class of the calling application. And then within that, each individual thread will have a relative priority level. Most gaming applications have a priority class of normal, meaning the threads range from between 1 and 15. Under certain circumstances, and we'll talk about this more in detail later, threads can actually have their priority level boosted. But with the exception of applications that have a real-time class, the actual maximum priority for a thread is actually 15. Most of this information actually comes from Windows internal. I've marked it in the top corner, and you can go into far greater detail than I could cover in the duration of this talk. The next thing to actually bear in mind is when Windows has threads to schedule, how does it go about deciding which ones to run? If we think of a very simple system where we just had a single CPU in the actual PC, you'd have a single ready queue. The ready queue would actually consist of 32 individual levels corresponding to each of the 32 potential priority levels of the threads. And at each priority level in the shared ready queue, you would have a FIFO list of threads that are currently ready to run. And Windows would actually work from the top, working through all threads of a particular priority level before moving on to the next level down. When a thread runs, it runs for an amount of time called a quantum, but this can actually be cut short by preemption. A couple of things to note. The system treats all threads with the same priority as equal. There is no attempt to share processes fairly among processes, only amongst threads. So if an application creates 10 times the number of threads, it will effectively get 10 times the amount of processing time. Obviously, this is no longer completely true for a much more complex system with hybrid. In theory, with up to 32 logical processors, you could have 32 ready queues, but this would actually increase the amount of contention when the hardware would need to actually lock threads on different queues when it was actually thread stealing. So instead, to try and simplify matters, Windows actually groups the threads into batches of 8. Each batch of cores have effectively what they call a shared ready queue, where those particular processes can run any of the threads within that ready queue. It reduces the amount of contention and the likelihood that a shared ready queue would have to thread steal from somewhere else in the system. A couple of basic scenarios for how threads get added to those ready queues. The first one is on wake. When a thread first wakes up, it'll be added to the very end of the shared ready queue, the FIFO list, for its particular priority level. The next one would be preemption. If a very high priority thread needs to run and a lower priority thread needs to actually be effectively stalled for a period of time, what happens? The OS will schedule the new higher priority thread and take the existing running thread and push that to the front of its list. So it will be the next one to run after the high priority thread completes. Another one to look at is obviously a voluntary switch. When a thread actually goes into a wait state, it no longer actually is part of the shared ready queue, instead dropping down to a wait state. And the OS will then pull the next thread from the start of the shared ready queue. The final one to bear in mind is what happens if a thread is long running and there is no interrupts. Eventually you'll hit a quantum end. At this point, a thread, because it's been running for a reasonable amount of time and the OS wants to effectively schedule additional time for other threads, the current running thread will be moved to the end of the linked list, its shared ready queue. This means it could be quite some time before that thread gets a chance to run again. The other thing to actually mention is this idea that while threads have their own individual priority levels, it's dynamic and they get boosted. Different things can boost the priority level, such as an event being pulsed, a timer set, hardware interrupts, and the OS itself manages things such as actually monitoring how long a thread has been waiting in a shared ready queue and potentially boosts its priority level, moving it up to a higher ranking. If a thread gets a chance to run for long enough and reaches the end of its quantum, then effectively the priority boost will gradually decay. There's a couple of things to note here. Looking at application, and I'll talk about this one in more detail later, Looking at a game that we had a thread pool where the worker threads all had a priority of 10. When I came to actually do data analysis, I never saw that thread run at priority level 10. It was always running at either 11 or 12 because it was actually being boosted in priority because of the number of events that were being pulsed on that thread. It does have a couple of knock-on side effects. If there's only a single level of priority difference between a thread pool within an application and maybe the primary thread or the render thread, it's quite often that the actual thread pool could actually end up with a higher priority than the actual long-running thread within the application, just because the long-running thread will have fewer events and will have less priority boosts. Another thing to bear in mind is Intel's thread director and how this fits into it. I mentioned it earlier. The idea behind thread director is to actually monitor the instruction mix. It does this by classifying the actual current instruction mix running on a particular thread. Generally, it will actually class it as default of 0. This would be a normal instruction mix. An instruction class of 2 would be a thread that had a high amount of ABX or SIMD code, while a class 3 would actually be a thread that actually had user mode weights in it. This is how Windows actually then figures out which cores fit best with the type of instructions that are currently executing. Intel's thread director only works on Windows 11 and above. Periodically, the OS and the actual hardware will update this table. Now, I think one thing to actually note is the table itself only affects threads of the same priority level. It by itself cannot actually have a low priority thread get a priority boost above a higher priority thread within the application. Another thing that's playing an increasingly important role within Windows is the idea of the Windows core parking engine. The idea here is, with the significantly higher amounts of resources that a modern PC has, it's suboptimal to be running all cores at exactly the same time. By parking some cores, you can actually dedicate more power to the remaining ones, potentially increasing the actual maximum turbo frequency of the remaining threads. In addition to this, it can also conserve battery life on things like mobile systems. So the core parking engine effectively enhances battery life, improves performance of the remaining threads, and allows the OS to prioritize shared resources like SMT for the remaining hardware that's in use. It's actually controlled by a couple of different variables. There is a minimum percentage for the number of logical processes that can be unparked at any given time, along with the maximum percentage for logical processes that can be unparked. So you have effectively, potentially, depending on the power plan that is currently running, you may not have all cores parked at any one time. The power plans also denote how often Windows can park and unpark individual cores. And the last one to bear in mind is the CP headroom. Just because there is a thread wanting to run and there is potentially a parked core doesn't automatically mean that Windows will unpark it. Generally, Windows will monitor how much work is available in the shared ready queues and then decide if it is worthwhile unparking a core, depending on how much work is expecting to be done in the near future. An example scenario of how Thread Director helps the OS figure out where to schedule individual threads. If there's a single thread running on a system, generally that thread would go to the first available P core. In a lightly threaded scenario, you can see here that first of all, Thread Director would actually denote to the OS the best place to run the individual threads would be one thread per P core, and then one thread per E core block. This maximizes the amount of cache available for any individual thread. Later on, when you've got a fully utilized system, you'll see all cores are used, but the last ones to be actually allocated are actually the siblings on the P cores. And finally, there is the low power scenario, where although there's only an individual thread to be run, Thread Director would indicate to the OS the best place to run this would actually be one of the E cores. The last thing to cover in this section is just what happens when Windows finds a thread waking up and it needs to figure out where to schedule it. The first thing the OS will actually do is ask the question, does it have any potential idle processes? It could be that all processes within the system are currently executing code, in which case the OS will have to figure out which active processor to add this thread to its shared ready queue. It does this by looking at the ideal processor the application is assigned to that thread, information internal, such as the last processor it was running on, so it can maximize cache coherency, and the feedback from Intel's thread director. On the other hand, if there are idle processors, the first thing it does is prune away any idle processors outside of that thread's thread priority mask. This could mean there's nothing else remaining, in which case we're back to scenario 1. On the other hand, there may still be idle processors available. The next thing the OS will do is check to make sure that they are not parked. It could be that all the idle processors the application can use are currently in a parked state. Just because of that, the OS will then attempt to try and unpark a core, but this isn't guaranteed to happen. As mentioned earlier, the OS will look at the headroom needed to unpark that core, and there is the potential that the ideal core the OS wants to unpark may not be usable by this particular thread, in which case we're still back to the actual scenario 1. Now, you can alter things slightly with set thread ideal processor. This will change one of the actual criteria the OS uses to decide which core to unpark. Now, we also have the option here, finally, that there are idle processors available, in which case the OS will decide which one to utilize. Again, using that set ideal processor, but also internal metrics such as the last processor used to maximize cache, information about the sibling usage of threads on the individual cores to maximize the hardware resources, and finally Intel's thread director feedback. So in these two scenarios, we've got a brand new logical processor available, in which case the thread would be assigned to the front of its shared ready queue. The final scenario here is if the OS is actually scheduling onto a thread that already has something running on it, in which case this is a priority check. If the thread's priority level is greater than the current priority level, it will preempt the existing thread, moving it to the actual front of the shared ready queue and effectively pausing it. Otherwise, the new thread will actually get added to the end of the shared ready queue. There's no guarantee at this point how long it will be before that thread gets a chance to run. So, to summarize that section, the first thing to bear in mind, the OS generally tries to schedule first with the P cores, followed by the E cores, and finally the SMT siblings. This is to avoid hardware contention of resources. The other thing to bear in mind is things like core parking. With the hardware getting more and more complex, the OS will actually use the power plans to denote how many cores it can park, and these power plans will differ between DC and AC scenarios. Do avoid things like hard affinities. I'll cover this more in the case studies, but as already mentioned, hard affinities limit the OS's ability to schedule on the available hardware, especially where core parking comes into play. Instead of using hard affinities, try to use the OS APIs such as setting quality of service, the set ideal processor, and if really necessary, things like CPU sets, which at least take into consideration the thread director guidance. The last thing to actually mention is workload scalability. Hybrid brings significantly more available resources, with far more threads that can be run in parallel by the application. Just because they're available doesn't necessarily mean all of them should be used at the same time. Obviously, we've already talked about a few things where the more threads that are running, obviously the reduced cache for each individual thread, and potentially the hardware resources are shared for siblings. So actually limiting the number of threads to get the best balance is actually the way to get the best possible performance. Okay, I'm moving on to data capture. I'm going to look at a few tools here. Intel's VTune and Microsoft's WPA, part of the Windows Performance Toolkit. To go with these, there is also GPU View, which is part of the Performance Toolkit, and Intel's Present One. All these tools are actually free to download and use. I'd also like to say thank you to IO Interactive. The data I'm presenting in this section actually comes from Hitman 3 and reproduced with the kind permission of IO Interactive. I'm using this purely to show how the profiling data is collected and how it's represented in the various tools. The application itself works well with the OS. There's no hidden gotchas. I'll save those for the case studies later. So the first thing to note, although I'm actually talking about actually optimizing for the CPU, the very first thing I always check is, am I GPU bound? Because if an application is GPU bound and the CPU is idling, waiting for the GPU to finish, it actually changes the state of the CPU. It will lower what's called its C states, potentially lowering the frequency. This in turn affects things like thread concurrency, how many threads are running at the same time, and potentially hides latency issues. So the way I usually do this is use Intel's PresentMon, which can be downloaded from GitHub. You can capture the GPU bound data directly through PresentMon using the command line that's highlighted at the top of this box, or you can use the Windows Performance Toolkit to capture a GPU view set of data, or XPerf, and effectively use the ETL file captured with that and then post-process it with PresentMon. Again, I've highlighted the command line here. PresentMon will generate effectively a CSV file, one line per frame within the game. There's a couple of interesting columns. The first one being the milliseconds between presents, effectively how long each frame is taking on the CPU. To go with this is the GPU timing data. This will tell us if we're GPU bound. The final one to actually note is the milliseconds until displayed. This is effectively the amount of latency between when something is processed on the CPU and when it finally gets drawn. I almost always take this CSV file and plot it as a graph. There's a few reasons for this. When you actually look at the overall frame, you can see here that the GPU is about 1 millisecond faster than the CPU for this particular benchmark. But there is big variations in the CPU frame time. There's also a couple of points in the frame where we get very high spikes, possibly related to I/O stalls or memory paging. Now, I always do this initially because when I actually open an ETL file and zoom into the behavior, I want to know if this is representative of the overall benchmark, or if I'm looking at a particular part of the benchmark which has odd behavior. How I look at the data will depend on if I'm trying to find out why something's different, or just understand the overall ability of the hardware to match to the OS. That same ETL file can be opened in GPU view, and this can provide a different slight viewpoint to the same set of data. You can see here in GPU view, we can see both the graphics queue and the compute queue on the GPU, and also from the applications point of view, the single main thread, which in Hitman is the limiting factor here, and the worker threads, and we can see dependencies between them. Now, from a CPU point of view, the most important thing I tend to look at when talking about a hybrid is the thread concurrency. WPA actually does a very good way of visualizing this. Now, I'll talk a little bit more detail here on the next couple of slides, but I'm looking here at the precise view in WPA as opposed to a sampled view. This is actually tracking the kernel level events inside the ETL file to give you a very fine-grained view of when threads start and stop. You can visualize this in a couple of different ways. Here I'm actually plotting the number of threads that are running at any one particular time. And you can see for Hitman, the majority of the time we have up to 8 threads running. This means most of this work should be going to the P cores. Later on, for those threads between 9 and 15, we'd actually have the P and the E cores running at the same time. It's only when we get more than 16 threads running that we'd be utilizing the P, the E, and the actual hyper-threaded cores. This was actually captured on a system with 8 P cores and 8 E cores. The view looks very different to something captured in VTune. It's only a small point to note, but VTune generally is a sampling-based application, and therefore, with a game where a frame might actually only take 2 or 3 milliseconds to complete, sampling at 1 or 2 milliseconds means you do not capture enough details to be able to understand exactly when threads are starting and stopping. WPA itself provides a wealth of different viewpoints. I'm going to just look at 5 here. So the first one is this CPU utilization. It's on the Graph Explorer tab, and under CPU usage, timeline by process and thread. And note this actually comes from this precise graph. A similar graph can be derived from the sampling capture, but the precise one is the one that includes the ETL data around the kernel level events. The second one that's interesting is again on the Graph Explorer tab, but further down under the Power drop-down, is the Processor Utility Processor Frequency Graph. And this gives real-time information about the exact frequencies the individual cores were running. You can see here the P cores were pretty constant running Hitman, where the E cores, because they have slightly less work, would occasionally drop frequency. In addition, core parking now plays a large role on how an application gets scheduled on the OS. And again, under the actual Power drop-down, there's the processor parking state, which tracks this at a very fine level. The last one to mention is actually the generic events. These cover the different providers within the system. The ones I usually look at are the direct X12 provider, which will show you where command lists got actually submitted, and also the kernel processor events. This will track everything, including changes within the parking engine or the power budget within the system. The nice thing about WPA is all of these graphs can be lined up one over the other. So you can see how the individual events correspond and how thread activity changes as cores get parked, and how this affects where actual events such as D3D command lists get executed. Now, that timeline by process and thread. A couple of pieces of information tend to be missing by default that I find really useful for analysing a game. I open up the settings, and you can see here I actually tick the CPU and the CPU usage. For CPU usage, I also changed the aggregation to actually do this by sum. This means that when looking at the table views in WPA, you can then sort the threads by CPU utilization. And so therefore you can actually find out which are the most expensive threads. Now, I also find it's rather useful to actually take this, and while it's a little bit of extra work, you can graph out all of this data from the table. By doing that, and knowing which cores are P cores and which cores are E cores, you can start to group things to see how much time individual threads within the system was spent running on the different core types. For Hitman, you can see that we have 2 threads that run almost exclusively on the P cores. Then we have a thread pool, which is split between P and E cores. Then we have the background threads that again tend to happen mostly on the P cores. Now, the other thing to actually look at when analysing this is to figure out how well Windows is dealing with the threads within the system. Now, this tends to be looking at the wait times to find out how long an individual thread needs to wait while other work is being done, but also the actual time spent in those ready queues. The idea being that hopefully on hybrid, the amount of time in the ready queues should drop. One thing I actually do is both the wait times and the ready times actually usually done in microseconds. So I usually change the format to milliseconds so that it can be viewed directly next to the CPU usage. I've noticed a couple of the older versions of WPA don't seem to change the headings on the fields. Newer versions seem to. Now, for things like this and understanding how well the OS is actually scheduling threads, it's hard to do if you're looking at a single system's worth of data. So I usually like to compare 2 different systems. Frequently when I'm dealing with the hybrid, one will be a non-hybrid system with just 8 P cores, and one will be a system with the P cores active, with the E cores active. So again, I've grouped just a couple of threads from Hitman. So I'm looking at really the game and render threads, which are the 2 most expensive that we saw on that graph, plus examples from the worker threads. Now we can look at both the time in the shared ready queue, how long each thread waits, along with potentially what's the maximum waiting time for that thread actually took. Comparing between hybrid and non-hybrid, we can see a couple of things. The first, that on hybrid, we're actually spending less time waiting in any of the threads, and the actual ready time, especially for the render thread, actually dropped. So increasing the actual thread count within the application has generally been a good thing in there for Hitman, and the main threads on the critical path all execute faster. In addition to that, we can see that the context switching for those two main threads drops fairly significantly from 9,000 on the render thread without E-cores to just over 6,500 on the hybrid system with the E-cores enabled. For this particular one, I'm using a single system and just toggling the E-cores on and off within the BIOS. You can also see that on hybrid, the maximum time any thread had to wait drops fairly significantly. Those context switches are important to understand. This is effectively when the OS decides it needs to swap what thread it is running on a particular logical processor. I normally capture most of my data using GPU view batch files. And this is effectively calling Perf with a set of providers. Usually I do the light format, which doesn't capture all of the actual CPU kernel level events. But it's enough to actually analyze the CPU and GPU workloads. But if I really want to dive in deeper to the application, then I'm going to need call stack data as well. And this is captured as part of the normal profile inside of GPU view. Inside of WPA, if you've done a capture that includes stack information, if you load the simples, then one of the fields available on that thread timeline view, which is the new thread stack, will suddenly be populated with valid data. This is the status of the thread, both when it last went to sleep, or another way of looking at it, when it next wakes up at the point of a context switch. By viewing the actual stack, you can see what the thread was doing and why it yielded. In this case, Hitman's render thread generally has a couple of different patterns. Frequently, it is executing all the way to quantum end. And you can see as you track down the call stack, there is no actual wait going on. It's running game code before a kernel level event is issued to actually then pause it. But there are also times within this thread where you can actually see that halfway down the call stack, there is actually a yield instruction where we call sleep. This is where the main render thread is actually deliberately waiting for the worker threads to complete. The other tool I need to look at is VTune. Now, often for VTune, and this actual slide came from last year's GDC deck, people talk about hotspot analysis and effectively marking up the code so you understand which functions are taking the most amount of time. It's really useful for this, but in my case, I'm really interested in the microarchitecture and analysis. One point to note, if you're actually collecting the microarchitectural analysis information, frequently it's best to disable virtualized based security inside the system's BIOS. Otherwise, not all the events are collected. But this will change the actual hardware slight performance. But it is a useful tool to actually then understand how individual cores are performing with the actual game benchmark. Now, one thing I also found out about VTune is I don't actually need to run it with the UI enabled. I can use the UI in VTune and actually build a command line to then actually do the data capture. I can either do this then from the command line while the application is running, or potentially even build a hotkey within the application that will trigger the collection for me. The metrics I tend to look at are really about the CPI, the clock ticks per instruction. To actually understand what's affecting this, usually the memory bound metrics are the next most important. So looking at cache bound and contested accesses. There are also some top level metrics like front and back end bound and data sharing metrics that can also be useful. Now, inside of VTune, if you do a microarchitectural analysis, if you do the bottom up analysis, you can actually go to the tools bar and do a custom grouping. One thing I usually do is group by process, then thread, then core type, which will split things between the P and E cores, and then the actual logical processor and function. This means on an individual thread level, I can see just how efficient it's running based on the core type it's currently executing on. For this particular thread, I can see that it was executing 0.849 clock ticks per instruction for the P cores and the slightly slower 0.962 when running on the E cores. But you can also look at the other metrics, so you can see the effect on things like the L2 cache as the actual thread migrates between the P and the E cores. Now, obviously, the cores themselves, clock ticks per instruction is great, but the cores themselves aren't running at the same frequency. But by taking that clock tick per instruction, inverting it, so you get instructions per clock tick, and multiplying out by the frequency, you can see how efficiently it was running each of the individual threads on the game, and the effect as it migrated. For Hitman, we can see here that the game and render thread are significantly more efficient on the P cores. I take this as meaning that these particular threads are really benefiting from the larger L2 caches that come with the P cores. In fact, this is the main reason why we increase the cache sizes for the P cores. It benefits these type of workloads. Meanwhile, those general purpose worker threads are running at about 60% of the performance on the E core relative to the P core. While the streaming and audio threads, there's almost no difference between them. Effectively, these are actually memory limited, so the core type doesn't actually matter. Now, the last one to actually say about this, though, is just looking at how efficient a core was running the code can be a little misleading. And this is one of the reasons I mentioned hyperthreading at the very start of the talk. For Hitman, when running with the E cores enabled, there is significantly less work run on those sibling threads. The OS is prioritizing using the E cores over the siblings. In fact, there's 33% less work done on the sibling cores. And this actually leads to anywhere between a 3 and 14% improvement for the code running on the P cores because it has less actual hardware contention. One of the final slides for VTune is we also talked about Intel Thread Director. And one thing people would like to understand is how is the hardware guided scheduler classifying the code within an application. Inside of VTune, you can actually do an analysis on the EHFI classes, which are those groupings. And you can see for the majority of games that I've analysed, the general purpose code comes out as class 0. So Thread Director itself isn't giving any particular guidance to the OS, other than saying, from a power point of view, how efficient the individual cores are. But it's not actually saying to actually send certain game threads to certain cores. This could change if you have a general purpose thread pool and you're mixing AVX heavy code in with general purpose code. There may potentially be benefits for splitting that. So AVX heavy code runs on its own threads so that those threads will get a different classification. And that brings me to our final section, the case studies. So a couple of points before I start these. The titles themselves are anonymous. They are also unoptimized for hybrid. I gathered this data during platform validation during early hybrid hardware. But it's also worth noting that all these titles actually do give a good experience on hybrid, even in the case where potentially they could do better. I'm using them purely to illustrate the OS's behavior on hybrid. So the first case study is actually one where the application benefits from hybrid. And it actually benefits by almost 10%. It's scaling very well. The thing that's interesting is the fact the application, despite having some very long-running threads that spend most of its time on P cores, overall it actually spends a significant amount of time running on E cores. This may not, while it's benefiting, it may actually be able to do better. It turns out this game is actually following a design pattern that I've seen repeated on multiple applications. It's actually creating several different thread pools. So in this case, there's a thread pool, a general purpose thread pool called the worker threads. There's a thread pool being used just for physics and another one for all the background work. You can see here that generally the worker threads and the physics run sequentially, while the background threads fill in the gaps when cores are idle while these other threads are active. And all of this is being managed by priority. You can see here the number of threads in each of the pools seems to actually be based on CPU topology. So it's creating exactly the same number of worker threads as physics threads. You can see here the background threads in theory don't actually take much time in this application. This is all about how priority and preemption works and how it changes on hybrid potentially. The application on a non-hybrid system was actually spending the priority 9 threads half of their time in those shared ready queues. You can see why when you look at one of the priority 9 threads, this one marked at the top, 5,252, you can see it's running and then it changes to a grey hashed area. This coincides with the higher priority thread, a higher priority 11 thread starting to run. Effectively, the priority 11 thread preempts the priority 9. That moves it to the shared ready queue. Now, on hybrid, things look very, very different. The first thing to note is the amount of time in the shared ready queue actually goes down by a factor of 10. The low priority threads no longer need to wait at all. If we actually view it in WPA and group the threads by priority level, you can see how they're all running here. Top priority level 15, the majority priority 11, and then the other groups for the priority 10 and priority 9 threads. And you can see where I've actually marked with the blue line, we do have periods during the frame now where we have up to 80% plus CPU utilization. And we have threads at all priority levels running at pretty much the same time. To summarize, if we dive deeply into the individual work of the frame, we can see that what's actually happening is low priority work runs in parallel with the high priority work. We can see here that there are cases where potentially high priority threads end up running on the E-cores when an E-core becomes available, but lower priority work is still in flight on existing P-cores. Potentially, this game could benefit from actually, rather than using priority purely to schedule, to actually physically defer the scheduling of the lower priority threads until all the high priority work is currently in flight. It could also move some of these background tasks to E-cores using something called EcoQuas, part of the Quality of Service API. The second case study is actually the complete flip side. This is an application that, while running well on hybrid, actually does see a performance regression when the E-cores are enabled. Looking at what the game actually does in terms of creating threads, you can see that on hybrid, it's actually doubling the number of threads created within its thread pool. And there's a couple of things to note. The first one being that most of the thread pool actually seems to take longer to run on hybrid despite having more threads, and that we have one of these long duration threads that spends half of its time actually running on an E-core. Looking at the reason why the worker threads take longer, first of all, we can see that, well, Amdahl's law suggests that if you double the number of cores, you'd effectively halve the amount of time taken to complete the work. That's not strictly going to be true because the E-cores and the P-cores have different performance profiles, but you would expect to gain. But that's definitely not happening in this case. The clue actually comes from actually looking inside of VTune and looking at those CPI metrics. You can see on hybrid, the clock ticks needed to complete a single instruction actually goes up fairly significantly. And the reason for that all comes down to memory bound. On hybrid, with all the additional threads running concurrently, we actually become significantly more L3 bound. Effectively, we've got data contention within the individual threads. The other thing to bear in mind is that one long duration thread that's spending time on E-cores. This comes down to the fact that the OS basically can't tell them apart from the actual worker threads. You can see here that there is one thread, 5,212, which looks very different to every other thread in the application. And this one does spend most of its time on a P-core. It's running at a slightly higher priority, and when it does run, it runs for a longer duration, 5.2 milliseconds plus. But the other long duration thread is actually running, well, say long duration, but the thread that spends the most amount of time running during the actual application, it actually is a priority 11, the same as the worker threads. And when it's running, it runs lots and lots and lots of short duration tasks, very much like the worker pool threads do. So from an OS point of view, you can't tell them apart. If we dive very deeply into just looking at a couple of those two threads, we can see this is basically what's happening. Thread 5,212 is actually waiting on thread 13,112. 13,112 is the thread that is running on both the P and the E cores. You can see here it actually context switches in the middle of a frame. It's basically when it does the context switch, the worker threads are also already active. So there's a high probability, because the OS can't tell it apart from any of the other worker threads, that it could be scheduled on one of the E-cores. It does that, and that then means that the work on there becomes part of the critical path, potentially increasing the priority of that secondary long-running thread would help, and also reducing the sheer number of worker threads would actually reduce memory contention, and potentially also allow the hardware to better utilize resources. The final case study is basically erratic behavior over time, when processor selection goes bad. Here we have an application that has two thread pools. The priority thread pool, which is very, very busy, and a secondary thread pool that is running AI. These two thread pools are completely decoupled. The expected behavior can be seen here in the middle. The AI threads wake up intermittently for a short amount of time and run in parallel with each other, effectively a very small fork join workload. But we're actually seeing frame rate stutters when this application was first analysed, and the frame rate stutters corresponded with the AI threads changing behavior. Looking at core parking, we could see that the thread pool's behavior changed as core parking increased. In fact, it was actually corresponding to effect if the OS parked more than 9 cores, the AI threads would start to misbehave. So why was this? If we look at a single frame from an AI point of view, it's taken 135 milliseconds, significantly longer than the 1 millisecond or less that it was taken when everything was running correctly. If we look a little bit in WPA, we can see that those 4 threads that the AI is running on, rather than working in parallel, are all running on exactly the same core, in this case, E-core 16. Core parking actually shows that that is the only unparked E-core. And it turned out one of the things the application was doing was using affinity to try and keep the AI separate from the other work within the main thread pool. So it's affinitizing the AI to the E-cores. Obviously, there's only one available here. That leads us to a second question. Why 35 milliseconds? That can actually be found out by looking at the thread weight reason within WPA. You can see here that all of these threads are actually executing all the way up to quantum end. So that they never actually yield in any way, shape or form. This basically comes down to a couple of things. The first one is, remember this? This is the actual what happened when a new thread wants to actually run within the application. It turns out with core parking, we had the majority of the cores parked, and the application was only had a limited number that it could actually use because it was using thread affinity. It turned out that all these cores were effectively running on 16 because that was the last available core the threads had run on. It was a case of the ideal thread that was assigned to all the AI was outside of its own affinity mask. So the OS was frequently potentially waking up a new core, but not being able to use it for this particular workload. The secondary fact was data contention. As soon as the application serialized all those individual threads, they actually ended up with data contention on a couple of structures within those threads. If the wrong thread ran first, it would basically block and wait until it hit quantum end, and eventually it would work its way around to the thread that actually held the data that was important. This was fixed by basically using set thread ideal processor, so the individual threads had an ideal processor within the affinity mask, and also later on removing some of the data contention issues. So even if we did serialize due to heavy core parking, the application could still make forward progress. So that brings me through to the closing thoughts. There's a couple of things. Hopefully you've seen there's a couple of, when looking at hybrid and analyzing the data, profiling is incredibly important. And free tools, both Retune and WPA, provide a wealth of information and how the OS is scheduling your threads. It's best to compare the data between systems with different core counts and different hardware hierarchies, because it will behave differently. I often take a single hybrid system and enable and disable cores to see how that affects the OS. There's a few APIs that become useful as you look at this. The quality of service APIs allow you to actually send certain work, such as background threads, to the eCores without the need to use hard affinity. That allows a lot more flexibility for the OS to schedule where it thinks is best. The other thing I've noticed is frequently don't oversubscribe the thread pool. This is in the two factors, like the one of the case studies where we had multiple thread pools using priority. That no longer works so well when you have so many more cores, but also just simply to reduce the amount of data contention and memory traffic actually within the system. The other thing to bear in mind, not explicitly mentioned, but avoid static partitioning. I've seen games that have thread pools where there is the hard assumption that each thread within the pool will execute roughly the same amount of work, with the P cores potentially much faster than the E cores, depending on the exact workload. It's best to allow dynamic partitioning of the work within your own application, therefore avoiding the need for the OS to thread steal between them. Another thing that's worth bearing in mind is also keep an eye on middleware. The OS treats all threads of one priority level as equal. That means you're also at the whim of your middleware. Understanding how the middleware is using threads and how other applications within the system are using threads is vitally important to understand how the OS is scheduling your application. Hopefully that has been informative. I'd like to say thank you, and I hope you've enjoyed the talk. Thank you very much.